Welcome to Kitchen Table Electronics, Module 1, Installing the Arduino. When you buy the Arduino, it will come in a box, and what you will notice is this gray-colored plastic wrapping. And this illustrates an important point about handling electronics in general. The reason this plastic is gray is that it is coated with a conducting film to avoid static charge building up on it. Modern integrated circuits have very tiny dimensions, and so the charge you can pick up on your fingers can be enough to ruin the chips. For this reason, they are packaged in anti-static containers, and you're advised to work on a surface that doesn't accumulate static charge. For example, a wooden surface, or alternatively, you can buy yourself an anti-static mat for a few dollars from any electronics supply place. This particular Arduino, which is the one I recommend in the hardware list, comes complete with its own USB connector. Here the USB-B connector that goes into the Arduino, and then a standard USB-A connector that goes into your computer. It's a fairly short lead, so you may want to make sure that your computer is somewhere convenient in relation to the space you're going to be working on. So here's what an Arduino board looks like up close. This here is the microprocessor. Here is the USB port that connects your computer to the microprocessor, and through which you will download your code to the Arduino microprocessor. In addition, you'll see several other things on the board. 10 here is the reset button. You press and hold this down for a few seconds and it will stop a program running on the Arduino if you're not connected to the computer. On the computer, you can do it from the Arduino IDE. We've got several other things on this board. This is a barrel connector for a 5.5/2.1 millimeter power supply with the central pin positive if you want to run this thing from an external power supply. The power can be taken from the USB, and the Arduino is wired with some intelligent circuitry that decides if the power available from the external socket is more than that from the USB, it will switch over. This here is a power regulator chip that provides from this pin here labeled 5 volts and this pin here labeled 3.3 volts a regulated voltage. What that means is it will stay pretty constant over a wide range of currents that you draw from these pins. These pins here are ground pins, so the voltage supply would be between here and ground or between here and ground. Ground is also the point where any input or output from the board is referred to. So for example, A0 is an analog input pin. It converts the analog voltage into a stream of digital numbers, as do these other pins here, 6 of them in all, A0 to A5. And you would put the signal in between here and ground. This is the crystal oscillator. There's actually a pair of them in here that provides the basic timing for the chip. The chip then contains circuits that takes the output of this and converts it in into the various sequencing operations needed to carry out the instructions. We have a number of light-emitting diodes on board the Arduino. In particular, this one here is connected to digital output pin 13. So you can write programs to switch this on and off from the Arduino development environment. So this is a LED you can control. What it does mean is that the use of pin 13 is a little bit restricted because it's internally connected to this light emitting diode. We have another ground over here. Over here we have something called AREF. It's the analog reference voltage, and it can be used to supply a reference with respect to which these analog measurements are made. I don't know that we're going to use that, but anyway, there it is. These pins here can be either input or output pins. You specify that with a pin mode statement in the development environment. So you can say pin mode input or pin mode output. for a particular pin number, and you do need to specify it. The pins are capable of being both, but if you don't specify, you won't be able to draw any current from the pin as an output pin, or very little indeed. These little LEDs here tell you when the chip is transmitting or receiving data via its serial bus. And I think that's about it for now. These little pins here are an SPI interface, so-called, which will let some other chip carry out some basic operations on the Arduino. So that collection of stuff looks like this to an electrical engineer. In fact, almost everything, these two blocks are not really separate blocks. They are all the microprocessor on board the Arduino. And what you can see is that the USB connector communicates directly with that chip. So these other chips on the circuit board have to do with voltage regulation and providing some control of the voltages that are both available externally and internally. Don't worry about complicated diagrams like this. As you build circuits in the class, you will understand the many components here, and then something like this won't look frightening. Although I promise you, an electrical engineer would spend a lot of time looking at this before they had it figured out. Okay, we are going to start off by installing the Arduino IDE. Missing from this video, because it didn't record, is the message that comes up from the Windows firewall saying, do you want to allow this application to make changes to your computer? To which you click yes. And it may come up and say that this application wishes to access things beyond the firewall. Do you wish it to allow it to? And you say yes. So we will do that. Once the IDE is installed, the driver, which is the software that communicates through the USB to your Arduino, should be installed too. So it should be seen as soon as you plug in the Arduino. More on that later. Under Tools, the IDE is set by default to the Arduino Uno, and it should show a COM port associated with it under the port setting. A COM port is the software that talks to the whatever is connected to your USB, and we'll talk about that a little more. But typically it has a number like COM3 or COM5, and you should see that when you look under the port setting in the IDE. If you have problems uploading a sketch, as an Arduino program is called, try the Get Board Info tool, and that should return the board details, meaning that the IDE is talking to your Arduino. And I'll show you how to go to the device manager on your Windows computer if you find there is a problem talking to the Arduino. So we'll take a look at doing just that. All right, let's go ahead and get our software. Okay, so we're going to go find Arduino. Google finds everything. Here we go. Right, we are going to go to Software. We're going to scroll down. Make sure you get the Windows installer. Don't go for the app or the zip file. Get the Windows installer. You don't have to make a contribution. You can hit Just Download. I've made a contribution for you. So click the Just Download button, agree to the license, and then start the install. And off it goes, extracting the files. And we're going to do a quick fade here so you don't have to watch the entire process. Okay, let's take a look. We finished the install. And what do we have? We have a new, recently added is Arduino. And up it comes. You get very familiar with this logo as you run the Arduino. And here we go. This is the environment in which you write Arduino sketches. And I'll tell you a little bit more about what all this means very soon. But anyway, let's take a look and see if we're talking to our Arduino board. Okay, so we're going to go and take a look here. Yes, there's the board, the Arduino Uno. And now we've remembered to plug it in. It wasn't plugged in before. And if we look now and get the board info, there it's telling us information about our board, so it's talking to the board. Okay. And you can see this board is on COM3. It could be on a different COM number on your computer, likely will be. What happens if you couldn't find the board when you did that? Well, type device driver into your Cortana window on your computer, go to the ports common LPT, and you should see the Arduino Uno connected on COM3. You can check the drivers and update them, and under the drivers tab, it'll say update drivers. It'll then search for the latest driver on the internet. And in this case, it says the best driver's already installed, so we're all done. We knew that. But do that if you can't communicate with your Arduino, once again through the device manager in Windows. So let's close those windows and let's go back to our Arduino. All right, so we've got it connected, and we are going to find an example sketch. So let's go to basics. Okay, Blink, which is the Hello World program of Arduino programming, and here it is. I'm not even going to bother spending time explaining this. It's a sort of self-loading program. We click the check mark and it compiles the program, and we click this arrow button and it will upload it to the Arduino board. Takes a little while, so we have a fade there, and we're still waiting for it to compile. You'll get messages here about the progress of the compilation, and then you'll see done uploading, at which point you have a working Arduino. So now let's go over to our Arduino and look at this. That LED, pin 13, is blinking as the program told it to. Now I pull out the connection to the mothership, the USB port, and I plug in the external power. And look at this. It remembers that you told it to blink. It keeps running that program unless you reset it. So this is one very powerful aspect of the Arduino. And it's designed indeed as a microcontroller to sit there doing a task, not really as a device to be communicated with by the computer, although that's how we're going to use it. So you saw there, we ran an example called Blink. We compiled it by hitting the checkmark button in the environment here, uploaded it with this button here. If we'd written it ourselves and made some mistakes, it would have told us after the compilation. But now let's write our own sketch to illustrate the absolute minimum that you perhaps can digest at this point about the Arduino. So I have called this My First Blink, and actually I went up here and saved it as a sketch. Sketches have the extension INO, and you will find them under Users, probably Documents, and then Arduino and Data, or maybe Data Arduino. But anyway, you'll find them on your computer. Each sketch or .ini file has to be contained in its appropriate folder. So beware, if you take sketches off the web or take them from somewhere else as .ini files, Arduino won't run them until they're in an appropriately labeled folder, and it's a bit tricky. So I like to cut and paste text into my Arduino IDE and then save it with whatever name I want to in whatever location I want to, and then you know the file folder structure is set up properly. But anyway, I've saved this as My First Blink. Actually, I typed in my space, first space, blink space, but it put the underscores in there because that's how Arduino likes to save things. These two little slashes here mean a comment. So I have put the minimum comment in here, just My First Blink, so I know what this program is. Now you'll see here there is a set of lines of code here called setup, and these two parentheses here tell you that setup is a function definition in C++. Void means it doesn't return anything, it just does something. This little open curly brace says this set of instructions that follows till the close curly brace belongs to this function setup. And whoa, we're being very complicated. We are using pin mode, and you see this turned orange because the IDE recommended it as, or recognized it as a keyword, 3, pin 3, and we're setting that to output. Wait a minute, you said. He just said that pin 13 was the LED pin. Aha, we're going to be clever, and we're also going to build our own little circuit. So we've now set pin 3 to be an output pin on the Arduino, and we've closed parentheses. This void loop always has to be present in every Arduino sketch. Even if you write hundreds of lines here, and this is the meat of the program, you still need a void loop with nothing in it at the end of the program because the Arduino expects it, and some of the communication goes wrong if you don't include it. So the other thing about void loop is this is a loop that goes on forever until you reset the Arduino. So it likes to be stuck in a loop, and that makes programming this, controlling this thing through the computer a little tricky, as we will see later. But thanks to the miracles of Python and PyFormata, we can get around that. So now we want to turn that pin on. Digital write, and you see once again the compiler has recognized this as a keyword. I remembered to type the capital W there. If you typed a small w, this wouldn't have turned orange. To pin 3, the state high, and that turns the LED on. Delay 1000, delay once again a keyword. 1000 means 1000 milliseconds, so it'll turn this LED on. It will then wait for a second, then digital write 3 low. So now it'll turn the LED off, and it'll wait for a second, and it will do it all over again. All right, so we upload this, we compile it, then we upload it, and let's see what we get. Before I do that, let's actually build our own first circuit. As I said, we're now going to drive pin 3. So before we had the onboard LED flashing on and off using the built-in Blink program, we've now A, written our own program, and B, we're going to wire our own circuit. We'll need a resistor. I happen to have chosen here a 1 kilo ohm resistor. You will learn to read these bands, but the brown means 1, the black means 0, and the red means 2. So it's 1, 0 times 10 to the power 2, or 1 kilo ohm. And we'll have more about reading resistor codes in a later section. But for now, I hope you've bought yourself an assortment of resistors and kept them in the packet so you know what values they are. It is in series with a light-emitting diode. This is going to be the positive side of the light-emitting diode. Pin 3 is going to produce a positive 5 volts to be applied to the diode. So, I should make that a little clear. This set of lines on the breadboard are connected together. So the top of this resistor goes to plus 5 volts, then to the LED, out through the LED, this jumper over here, which you don't need really, just put that in for clarity. You could have had the green wire going straight here, back to the ground connection on the Arduino. So it's a resistor and a light emitting diode in series. One little trick you need to know is that for this diode to turn on, this positive side here, so it's going through here, through the resistor here, needs to be connected to the anode of the diode, and I'll show you how to find that in a minute. This is the cathode, and that is what needs to be connected to ground. So this is what it looks like in a schematic. By the way, this last image here came from this software Fritzing, and then I just simply clicked on the page to show the schematic. And so here you see digital pin 3. We connect through this 1 kilo ohm resistor. Here's our LED, and this symbol means anode, and this means cathode, and we go through to ground. For the LED, you find the anode and the cathode by holding the thing up to the light and looking through it. So this picture is a clear LED. Your LED will likely be red. And what you'll see is a big connector. This is the cathode, and the little one, this is the anode. If you get it wrong, no harm done, it just won't work. You want to take it out and put it in the other way. So this is what it now looks like. Here is my wire to the ground going to the cathode of the LED. Here is the anode, and it is connected to the resistor here. You can't see that wire going into the board very clearly, but it comes down here and is connected across this way through the resistor, through this red lead, and it goes to digital pin 3 on the Uno board. Just a few side words about these breadboards. These lines here are all connected together, but one row is not connected to the next row. So you can connect components together by having them lie on the same row, and then you can have different leads going into adjacent rows. All right, so we wrote the sketch, we uploaded it to the board, we've wired our circuit up. As a general rule, I would disconnect the Arduino when you connect a circuit to it, and then plug it into your computer. And what do you get? Let's see what we got. Look at that. We are now blinking the external LED. Let's just look at that again because we're so proud of what we did. Okay, we made our first Arduino circuit work. Now I want to jump off the deep end and talk about datasheets. We're going to use datasheets all the time. Electronic components can be very complicated, and this microprocessor is probably the most complicated thing, certainly the most complicated thing you will work with. But just like everything else, the manufacturer wants you to use them, and they provide very comprehensive datasheets. So this thing, I think, is several hundred pages. I put a link to it on the blog site. But let's just jump into it and see what it's telling us and see if we can understand at least some of the words on it. And then for simple components, you'll use a lot more information on the datasheet. Now, here we start off by being told there are 131 powerful instructions. What this means is programmed into the wiring of the chip itself, there are a total of 131 instructions. So you can send in the machine level language, a number to the computer that says use instruction number 130 and apply it between a number in register 1 and a number in register 8, let's say. It's got 32 8-bit general purpose working registers. 8 bits means that there are 8 binary states of ones or zeros. So a total of 2 to the power 8 as a possible number that could be held in that register. There are 32 of these registers, and they can all be manipulated for storing intermediate parts of calculations. It's got 32 kilobytes of programmable flash memory, which is where you'll download your sketches to. It has an erasable programmable read-only memory, which is something you can externally program, but not through the serial port, and it will hold memory until you erase it. And then actually inside the instrument itself is another 2 kilobytes of so-called static random access memory, which is where intermediate parts of the calculation are kept. The in-system programming by on-chip boot program means it's got a place to tell the chip how to start. It needs to know to communicate through the USB port or wherever, and it needs to be sitting there waiting for instructions ready to communicate from the outside world to this set of instructions loaded on the machine. And that's what the boot program's for. Just a comment here, if you decide to save even a few more dollars by going for an even cheaper Arduino, you might find it does not have the boot program on board, and then you have to load it yourself, which is a bit of a hassle. So make sure to read the FAQs on the website where you buy the chip, and make sure that it is completely Arduino compatible with the boot program on board. This tells you the configuration of it. We've talked about some of these things, although you notice there are more lines available than are on the board. But what is this USART thing? Well, that stands for a Universal Synchronous Asynchronous Receiver Transmitter. This is the block of hardware inside the chip that communicates with the USB port. ADC stands for Analog to Digital Converter. There is one, and it converts the input into a 10-bit number. You can change that, by the way, in external programming. ADC channels 8, we mentioned 6, so there are 2 obviously here that are not used. The ADC is actually multiplex, meaning it'll go and look at 1 pin, and then if you tell it to do 2 conversions, it'll swap back and forth between the 2 pins and so on. So you degrade the performance as you read more channels in. These counter timers are there to take that very high frequency from the crystal oscillator on board the Arduino board and divide it by some amount to set timing cycles for inside the chip. This is a block diagram, and oh, good heavens, I've mentioned some of the components here, but you can see that the overall layout is really quite complicated, and we won't worry about it for now. But nonetheless, if you study the data sheet, if you do want to get down to the level of controlling precisely what happens at certain points on the chip, enough study of the data sheet will get you there. It is not magic. It's just complicated. And here's what the chip actually looks like. So these are the pins. You'll notice it's got two positive voltage supplies here, one for the digital side and one for the analog side. And that is to keep noise on the analog side down. And let me see, does it identify the ground pins? Yes, here we go. Ground and ground are the black pins. And then these are the other input and output pins and serial communication pins and the pins for the crystal oscillator. More on the data sheet. Let me just say, whatever chip, transistor, or whatever you download, go and search for this bit, absolute maximum ratings. So we've had to go all the way to section 32 in this very large data sheet to find this. But, and it's very important. Now, notice this. It will only tolerate a voltage on any pin, except reset, between negative half a volt with respect to ground. So it doesn't mind being biased slightly negative. We'll see, by the way, why this magic number of half a volt is there later on when we talk about transistors. All the way up to whatever the supply voltage is, which is typically 5 volts, plus half a volt. So any pin can be biased between minus 0.5 volts up to, say, 5.5 volts. And to be safe, you want to keep it between, say, 0 and 5, absolute maximum. You simply cannot put a bigger voltage on a pin or you will blow it up. So this is a very important thing to look at with any chip. Down here, it's got the output from the current regulated pins. Actually, I see here it doesn't want to give more than 200 milliamps. Maybe it's the Arduino board that can conceivably give up to half an amp. But if you try and draw power from the chip, you can't draw more than 200 milliamps, I see. Now, you can draw from each pin only up to 40 milliamps. Over here, it shows you the definition of the logic states. So if you want logic 0 on a pin, what is that? Well, we're going to be operating at a applied voltage VCC, certainly around 5 volts. And that tells you that the minimum to have a low voltage is minus half a volt. Well, we knew that. We knew we couldn't go below minus half a volt. We can obviously 0 is a logic 0. But we can go up to 1/3 of whatever the applied voltage is. So 5 volts divided by 3 will still just be a low state. All right, let's take a look at the high state, which is the logic 1. This tells us that this starts at 0.6 VCC as a minimum. So that would be 3 volts if we have a 5 volt supply, and can go up all the way to VCC plus half a volt or 5.5 volts. You'll notice that there's a gap in the middle between 0.3 of VCC and 0.6. This is the hysteresis in the logic that means that noise won't accidentally trigger the logic from one state to another. So here you see you've learned a lot about what you can and can't do with this device from the data sheet, even although most of the data sheet at this point should be truly unintelligible. Of course, we can get data sheets for simple things. So this is the LED I happened to use. And this tells us something about the maximum currents I can put forward through it. What else does it tell? Power dissipation I'm allowed to have. Somewhere it should tell me what the voltage across it typically is, but I see I didn't copy that bit. Here are the dimensions of the case for the LED and so on. All right, so we're done. We have learned to install our IDE. We've used an example program to make the Arduino run Blink. We've shown that we can run Blink either with the power coming from the USB or disconnect the mother computer altogether and have the Arduino continue to run the program on an external power source. I used a little 9-volt wall plug-in power supply, 9 volts DC with the central pin positive, and plugged that in instead of the USB, and the Uno kept running perfectly happily, which is an illustration of what the Uno was meant to do. Here's a list of the hardware. You'll find this on the blog homepage. I just want to make one comment about hardware while I'm here. You may buy, as I suggest, a set of wires with connector pins on the end. But if you do decide to make your own wires, and you'll have to do this for at least one of the projects that we cover very soon, buy 22 gauge wire and strip the plastic away to make a bare end, but leave more than you think you should. I strip about 1 inch. Why is this? Well, when you plug it into the breadboard or these sockets on the Uno, you want bare wire sticking out. Why is that? The weak point is right here where you used your wire strippers to cut the insulation off. And this is the point where these wires tend to break. So at some point, as you plug this in and out of things, it will break here. Now, if it breaks here and you've got wire sticking out of the socket, good. If you push it all the way down and it breaks, bad. I have done this. Please don't fall victim like I did, and I had to go out and buy another Uno because I could not get that piece of wire out, despite the helpful hints on this topic to be found on the web. So that's it. You now know how to run your Uno. We are now going to turn to some extra electronic tools in the next lesson.